So today I'm going to do a very brief and I think simple introduction to what is called single molecule experiments. So single molecule techniques are very interesting techniques because they allow us to manipulate and observe one molecule at a time. So to illustrate the importance of this, let's do an analogy. So imagine we are on a plane looking at a marathon and the image you will see will be probably similar to the one behind me, but from our observation, we could only see how the whole crowd is moving. We could calculate the velocity which the crowd is running, but that we could call the average velocity of a runner. But of course, if you want to win the marathon, you have to be the fastest of all. That means that your velocity is going to be much higher than the mean. We also know that in a marathon, there will be people that run slower or that will even have to stop to catch their breath. But we cannot see this from our plane. We can only see how the crowd is moving. So now we go back to biophysics. Let's say I want to study an helicase, which is actually what I do. An helicase is a protein that unwinds the double helix of the DNA. And now let's say that I want to calculate the velocity at which this helicase is opening my DNA. From what it's called a bulk or an ensemble technique, where I have lots of proteins and lots of molecules, I will only obtain the average unwinding rate of my helicase. That's a good thing, but I will probably miss some details, such as, does my helicase go faster sometimes? Does it have to stop at some point? But if I instead do what it's called the single molecule, okay, so if I instead perform a single molecule technique, I will be able to track down very precisely how one single helicase is opening one single molecule of DNA. And that is very impressive. So how can we do this? Well, there are many single molecule techniques that I can apply, but I'm going to focus to the one I use in our lab. It's the one called optical tweezers, and it's a very powerful instrument because it allows us to apply forces from 1/10 up to 100 piconewtons and to measure distances about 1 nanometer. So here you can see an image of the scheme of the experimental setup and the real image that we can see in our lab through a microscope. So the basic idea of an optical tweezer is that we have two laser beam focus that create what is called an optical trap. And with the energy of the light, we are able to trap small objects like this micron-sized bead that you see here. So just that you get an idea, what we can do